So where we've been so far is we've been talking about a system which is in contact with a reservoir at some temperature T. So that means the system is in thermal equilibrium with temperature T. And what we've been talking about is if that system has some energy states, like the ones that are shown on the right here, so the system has some energy levels or some different states that the system can be in, if the system is in contact with a reservoir at temperature T, what's the probability that the system spends its time in state 1, state psi 1, state psi 2, and so on? So basically we're wondering what's the probability that you find the system in some particular state given that it's in thermal equilibrium at some temperature T. And we worked out in the last set of lecture slides that this probability that the system is in state psi 1 is proportional to this factor, e to the minus the energy of state psi 1 over kb times t. So this is the kind of main result that we've had so far. We've learned about this proportionality. So this here is the probability that the system is in state psi 1. It depends on the energy of state psi 1, so this would be like, this would be energy E1, this would be energy E2, E3, so on. Okay, so basically in this lecture what we want to do is go a little bit further. We want to flush this out a little bit more. In particular, I want to know what is this proportionality. So I want to know exactly what is the probability equal to, not just the proportionality. So I want to deal with more than just ratios of probabilities, but how do I actually calculate the probability? And for that, you need this thing called the partition function, which is usually called the letter Z. And so we'll learn how to calculate that and also learn what it's good for. In addition to calculating probabilities, it's also extremely useful for calculating thermodynamic properties of the system. So in a sense, this lecture is bringing everything full circle. We're doing some statistical mechanics, learning about probabilities and statistical properties of the system, and then we're going to be able to connect that to the stuff we've done earlier in the course, thermodynamics, learning about the average energy, the entropy of the system. And so that's, in this sense, we're connecting the two parts of the course, thermodynamics and statistical mechanics. So we're considering a system which is in thermal equilibrium at some temperature, T, and it has some energy levels and energy states, and we're talking about the probability that you find the system with some energy EI, so I labels the state. And we've argued the last time that the probability is proportional to GI times e to the minus EI over kBt. And GI was the degeneracy factor, so this is degeneracy, which is equal to the number of states with energy EI. So if I make this a little more, write this in a little more detail, instead of proportional to, that means it's equal to some constant times GI e to the minus EI over kBt. And by constant, I mean it has to be something, it doesn't mean it's a pure number, but it means it's independent of I, so it's common to all states. So when I took the ratio of the probabilities in the previous lecture, that thing cancels out because it's the same for all states. And by convention, this thing out in front here is just defined, we're going to give it a name, and the name is 1 over z, and that's just convention. So then I have P of EI is 1 over z, no longer proportional, it's equal to 1 over z times GI e to the minus EI over kBt. Okay, I'll come back in a second to why it's called 1 over z, but let's think for a second about how to calculate it. So this is a probability, right? It's a probability that is found in state EI. And what you know about probabilities is, this is the key idea of the whole lecture. It's a very simple idea. When you add up all the probabilities of all the energy states, it's got to add up to 1, right? Probabilities have to add up to 1. So it means that the probabilities must add to 1, or in other words, you can't have more than 100% or less than 100% probability. You got to find the system somewhere, and if you add up all those probabilities, you should get 100% or 1. So that means that the sum over I, add up all the energy levels, probability that it's in state EI, must add to 1. Okay? And therefore, if I write this, let me take this a little bit further. So I'll put here 1 over z, sum over I, gi e to the minus ei, whoops, over kbt, just like that, equals to 1. Now the z here is common to all states, right? It doesn't depend on I. It's independent of I. So it comes outside of the sum. So 1 over z is equal to sum over, well, let's do it slowly. Sum over I, gi e to the minus ei over kbt equals to 1, which means that z is equal to the sum over all states, I, or sum over all energy levels, gi e to the minus ei over kbt. This z is sometimes called, well, in English, it's called the partition function. And that's the kind of constant of proportionality that makes it so all the probabilities add up to 1. So this thing called the partition function is found by summing up all of the energy levels, this factor here. So I is running over all energy levels. To get a sense of what this might look like, let me just make up some energy levels for a particular system. So let's say, for example, my system looks something like this. Okay, so this will be E1, this will be E2, this will be E3. And let's just label each of these states. Okay, so I just made up a system which has 1 state with energy E1, 3 states with energy E2, and so on. So in this particular state, my z would be, so this is example, toy example, would be add up all of these e to the minus e over kt for each energy level multiplied by the degeneracy. So it would be g1 e to the minus e1 over kbt plus g2 e to the minus e2 over kbt plus g3 e to the minus e3 over kbt. Now g1 is 1, g2 is 3, g3 is 2. So that simplifies this a little bit. So like this. So I just plugged in the numbers for g2 and g3 and g1. And let me do something which seems kind of silly, but let me write out that factor of 3 as 3 separate terms. So I wrote it out so that there's no factor of 3 or factor of 2 anymore. So you can see all of these here have energy E2, and all of these here have energy E3. So these are the levels which have energy E2. These are the levels which have energy E3. And you notice there's 3 of them because there's 3 states with energy E2. So this might be the state psi 2a. This might be the state psi 2b, psi 2c. This would be psi 3a, psi 3b. So what I'm doing, and this of course would be psi 1. So one way to think of this sum is, one way to think of it is this way, adding up all the energies multiplying by GI. But another way to think about it is just adding up all the states and taking e to the minus e of that energy of that state divided by kBt. So another way of writing this Z is sum over all states. Not energy levels, all states. Right? So this, in this case, in this example, there's 1, 2, 3, 4, 5, 6 states. That means there's 6 terms in the sum, and we wrote them all out here. Sum over all states, e to the minus ei, energy of that state divided by kBt. It's the same answer as above, it's just a different way of framing it. Sum over all states. And this is, now I can explain why it's called Z, because it came from German. And so Z in German stands for Zustand Sum, which means, if you translate it from the German, means sum over states. So what you're doing is you're adding up this factor over all of the energy states for the system, making it so the probabilities add to 1. I like this much better in German than the English word partition function is much less clear. Z Zustandsum, the sum over all states, is much clearer what's going on here.